Today we're looking at Exploration 3.5, Velocity and Acceleration Reading, and it's really to get a better idea of the relationship between velocity and acceleration, and especially in the context of calculus. Now for this exploration, you will need your graphing calculator, so if you don't have that, you might want to go dig it out, put it on your desk with you. First question is, what's the difference between displacement of an object and the distance it travels while it's in motion? The only difference is really displacement will give us a direction, meaning the object went forward versus backwards, whereas the distance it travels is always going to be a positive value. It does not tell you whether the object traveled forwards or backwards. So for displacement, it has a sign. It has a direction. Which means positive and negative have some significance. However, when we're talking about distance, distance is always positive, so it does not give a direction. So now we're going to move on to relate velocity and speed. If you notice your speedometer in your car, it doesn't have negative values. So if you are going backwards, it's still going to give you a positive speed. However, when we're discussing velocity, we know that velocity is signed. It's either positive or negative. Positive would mean you're moving forward, negative would mean you're moving backwards. So for velocity, it is signed and it gives a direction. Now, a velocity and a speed are also telling us how fast something is going. And our speed does not give direction, and it's always positive. So number 3, if the displacement of a moving object is given by y equals f of t, t is time, write 3 different symbols for the velocity. Well, the velocity is going to be the rate of change of the displacement. And again, displacement was signed and velocity was signed, so our rate of change of displacement will also be signed. So first of all, it's called y equals f of t. So we're talking about the rate of change, which is the derivative. And we know how to label a derivative. A derivative could be called y prime. A derivative could also be called f prime of t. Additionally, we could write it in a rate of change format, which would be the change in y over the change in t, so dy dt, or we could reference it as an operation, which is the derivative with respect to t of y. Any of those would represent the velocity if we were given the displacement. Number 4, if the velocity of a moving object is given by v equals g of t, write 3 different symbols for the acceleration. Well, how's the acceleration related to the velocity? Well, the acceleration gives us the rate of change of the velocity. How quickly is our speed changing over time? So again, we're going to be signed, and we also want the derivative, which means we're now going to have notation for our derivative. So if we started with v equals g of t, the derivative of v would simply be called v prime. The derivative of g would be called g prime of t. And again, we can have the rate of change of v with respect to time, or dv dt, or we could have the operation d dt, the rate of change with respect to time of v. Number 5 is now skipping a step, so to speak. So the acceleration A is going to be the second derivative of the displacement. If you notice, when we started with displacement, we took the derivative to get the velocity. When we started with the velocity, we took the derivative to get the acceleration. So if we start with displacement, the second derivative of that will be the acceleration. So again, we are signed. We're going to write different symbols for the acceleration as a second derivative. So we want the second derivative now. And again, because it's a second derivative, we're just going to add on a prime for the beginning. So instead of y prime, we're going to have y double prime, second derivative. Instead of f prime of t, we're going to have f double prime of t. Now the notation for the second derivative in the rate of change format is d squared y over dt squared. And the reason it looks like that is if we write it as an operation, we're taking the second derivative with respect to t twice of y. Moving on to number 6. True or false? If the acceleration of a moving object is negative, then the object is slowing down. Justify your answer. So let's think about this as if we were in a car. I'm driving forward, but I'm approaching a stoplight, which means I want to slow down, which means I put my foot on the brake, which causes my velocity to decrease, which means my acceleration would be negative. So in that case, the acceleration that is negative is causing my car to slow down. However, what the acceleration, a negative acceleration is doing, it is trying to get the car to go in the other direction. So if you're moving forward and you have a negative velocity, it's trying to take it to go to the negative direction, which would be backwards. Which means if I'm actually going backwards, I have a negative velocity, and I add in a negative acceleration, that's actually increasing my speed because my rate of change of my velocity, which is already going in a negative direction, is negative, making it more steep. So what we need is we need to have the signs to be opposite in order to be slowing down. So the answer to this is actually false. And the key is, if my acceleration is negative while my velocity is negative, then the object's actually speeding up. So when I have different signs of velocity and acceleration, that means I'm slowing down. They're working against each other, the acceleration and the velocity. However, if I have the same signs for velocity and acceleration, then, sorry, that's an A, not a C, then that means we're speeding up. They're working in the same direction to increase the speed of the car. Number 7, we have a particle that's moving along the x-axis with displacement x feet from the origin given as a function of t seconds by x equals t cubed minus 9t squared plus 23t minus 15. What is meant by a particle? A particle is just an object. We usually say it's a small object, but the key is it's just some object that's moving. Number 8, write an equation for the velocity of the particle in problem 7. Well, what was this equation in problem 7? We have this thing right here, and that represents the displacement. So if I want the velocity is the rate of change of displacement, which means the velocity is actually the derivative. So my velocity is going to be the derivative, which is going to be 3t squared minus 18t plus 23. Number 9 now wants us to actually graph the displacement in parametric mode in our calculator. So everyone's calculator should be on. Let's go ahead and change our mode. So press mode right next to the blue button, the blue second. And where it says function, we're going to change that to parametric. Maybe. sorry. So I'm in parametric mode, and when you now press y equals, it looks very different. We have an x, we have a y, and we have x1 and a y1 and this little t underneath. So what we're doing was we're putting something in for x, we're putting something in for y, and our variable is actually going to be this other thing, t. Now we're not going to use this for anything other than demonstration purposes. So all we're trying to do by graphing a parametric is to look at this displacement equation and try and mimic what the object's actually doing. Because when I look at that equation, is the object moving to the left? Is it moving to the right? When? I don't know. So we're going to graph in parametric just to see what it looks like. So for x, I'm going to put that into x1 sub t. So that's just t cubed minus 9t squared. That didn't work. T Okay, I don't know what this is doing. Okay, so I have keyed in the equation for x into x sub 1. If you read the directions in number 9, it says with y equals to 1. So it says with your graph in parametric mode, plot x as a function of t with y equals 1. So we're going to go down to y equals 1, y equals, sorry, and enter a 1. And now you can see that we have the each of the equal signs are now bolded in black. So it has a window for me. So what we need to do is go to our window now, and it says our t domain is from 0 to 7. So make your t min 0, your t max 7. T step, not really relevant, 0.1 is probably good. Our x domain should be negative 20 to 20. And our y domain should be from 0 to 2. So again, all I did was put the window in the way it was described in the question. Now it does want us to set the grapher for path style. So when you go back into y equals, if you arrow over so that you are to the left of the x, it was a slanted line, hit enter, and it moves to a bold line, hit enter again, and it now has this open circle. That's the path that we want. If we put the open circle without the line, that means I'm not going to actually get a curve out of the thing. So we can do it either way. And again, this is dashed. I'm just hitting enter to cycle through again. That's how it originally is, the bold line. This is going to leave a path in its place, and the other one is not. I'm going to leave mine right here. What I'm going to do is hit graph, and I need to watch what happens. So the object moves to the right, the object moves to the left, the object moves to the right again, and goes off of the screen. So the question says, describe the motion that you see. So what I'd like to do is actually get a little more specific. So I'm going to hit the trace button. Now the tricky thing about the trace button is that we need to actually always arrow to the right. No matter what the object is doing, you have to arrow to the right to make the time increase. So what I would say right now is I would say, well, the object starts at x equals negative 15. So go ahead and write that part down. Starts at x equals negative 15. Then I'm going to press the right arrow button and notice that it's moving in what direction? It's moving to the right. So I'm going to write that down. It moves to the right. And then I want you to keep doing this until you can tell it's not moving right anymore. So I keep arrowing over, and I'm looking for when my x values aren't increasing anymore. Oh, that just happened. I missed it. So I'm going to go backwards. And I think 307 was as big as my x values got. So at approximately 3.1 maybe, the object is going to stop. And after it stops, as we keep hitting the button on the right, the object is now moving to the left. So the object moves left, and I just keep hitting the arrow button, and it stopped again. And it stopped again at, looks like, the same place, about negative 3.07. I would again call that about x equals negative 3. Then it moves again to the right, and it appears that that goes on infinitely. My x values are continuing to go up. So you should have written that down as we were working. What I'm going to do right now is I'm going to pause. I'm going to pause my video, and I'm going to write the answer that I would expect to see for number 9. So for number 9, it starts at approximately x equals negative 15. That actually was exact. Moves to the right until stopped at x is approximately 3.1, then moves left until stopped at approximately x is negative 3.1, then it moves right again infinitely. So for number 10, at t equals 2, what are the velocity and acceleration of the particle? And is the particle speeding up or slowing down at this time? At what rate? And justify your answer. So for number 10, the first thing I need to know is the velocity at 2. I already have a velocity equation, and it's right here. So I'm just going to use that. So my velocity at 2 is going to be 3 times 2 squared minus 18 times 2 plus 23. And when I work that on my calculator, I got that to be negative 1. I need units on this, so I go back to the problem in number 7. And in number 7, it should tell me what my units are. And my units are x feet from the origin and given as a function of t seconds. So those are my units that I would like to use. So it's negative 1 feet per second. The next thing I need is the acceleration at that time. Well, I don't even have an equation for the acceleration. So first thing I need to do is write an acceleration equation. The acceleration is going to be the derivative of the velocity, which I have in green above in number 8. So that's going to be my acceleration, and that will be 6t minus 18. Now I can find a at 2, which is 6 times 2 minus 18, which is negative 6, and the units for acceleration will be feet per second squared. So now I have my velocity at 2 is negative 1 feet per second. My acceleration at 2 is negative 6 feet per second squared. So is this particle speeding up or slowing down? At what rate? And justify your answer. So all I really need to care about are the signs. The velocity is negative at this time, which means the object is moving backwards. The acceleration is negative, which means it's also trying to take the object backwards, which means this thing is speeding up at t equals 2. And I know this because the signs of velocity and acceleration are the same at t equals 2. Now it also said at what rate is it speeding up? I'm going to write that right down here. It's speeding up at a rate of 1 foot per second. And then the last question is, what did you learn as a result of this exploration? Feel free to fill that in. Give yourselves any notes that you need on this topic. I hope you have a nice evening, and we'll go over any questions in class.